So this model, so this model that we're looking at here, or that we were looking at, this model of infection spread, what other phenomena does this describe? Where else do we see a process like this? Some people may have borrowed the Business Dynamics book, and this model features in other areas in there as well. Where else do you see a process like this, besides spread of infection? Give me some other cases where you see similar phenomena or similar processes like that. Percolation process. Processes where there's a spread of X. What else spreads? Maybe from person to person. You're young people. You use the thing called, a rumor. Yes, a rumor can spread exactly this sort of way. And people use these models to describe rumor spread. A thing called a tweet can be spread this sort of way, right? You get a tweet and you pass it on. I think it's called retweet, right? So there's a spread of information like this. What else spreads? Sorry? Fire. Yes. So fire catches and can spread in this sort of way. In fact, that's a very close analogy to what we're seeing here. Because the fuel for the fire here is the number of susceptibles. And eventually, if this fuel gets burnt up, if it gets exhausted, or as it gets smaller numbers, there's more and more ash and less wood to burn, you're going to get less and less spread here. So that's a good example. So fire would be another thing. What other processes have spread?
Flood.
Yes, that's right, flooding. So to a degree, so what might happen if, for example, a flood, you could think of that as contagion. I mean, with flood, you don't normally think of water as multiplying, like it doesn't, like one liter doesn't become 2 liters, 3 or whatever. But what it can do is, like, a flood might break down flood control measures. Like, it might destroy floodgates if it's really pronounced, to destroy berms or destroy barriers to the flood spreading, and that might lead to the flood to spread elsewhere. So, for example, in Thailand, about 2 years ago, a little bit less than 2 years ago, the flood spread throughout Bangkok, and they ended up doing all sorts of weird things, and they'd pop up in places people didn't expect. Like one day, one neighborhood would flood, and they'd go and they'd try to fix it, and then the flood would pop up in another place. It was very strange sort of behavior. Come up through sewer grates, and it might destroy things which allow it to spread. So yeah, flood has some things. What other things might spread? Pollutants in the water. Okay, yeah. Certain types of pollutants, like biological pollutants, in a big way. Something like microorganisms that spread. In other words, they can infect people. For example, cholera bacteria, for example, can spread. And there may be certain types of toxins that will kill off plants that would otherwise clean the water, and so you get this kind of breakdown of the natural defenses, and therefore spread of the toxins at higher levels than they otherwise would have been, because the things that break them down or immobilize them are no longer present. So that's an interesting case. Innovation spread. People use these sort of models to study how innovation spread within a company, how innovation spread within society, how people start buying consumer product like the iPhone 5 or what have you. How that spreads from person to person. People see others with it. They want to get one themselves or what have you, and you get a very similar process of infection spread. So these sort of models, they may look very simple. They may look very sort of focused on a particular area. After all, we label it susceptible, effective, or covered. But these could be people susceptible to sort of interest in buying an iPhone. Infective are those with iPhones telling other people about it, showing it to others and so on. And recovered are people, well, they've had the iPhone, but they've had it for a while, and they're no longer going around and saying, wow, look, this is something interesting. So they'll be on the stage where they're actively sort of influencing others, something along those lines. Or maybe they're no longer interested in buying. So here we have a model which actually goes by different names in different contexts. It's most classically known in the SIR context, but you'll find the same model type popping up in business, for example, under different names, etc. So it's very important. It's a very important model, and it's important also for improving understanding of, and for sort of demonstrating some understanding of stocks and flows. So I would like to take you to some slides here where we're going to be talking about its behavior. Okay, so where are these slides? Here. So we're going to take a look at behavior over time, and I'm going to do it in a way, I want to do it without these hints present. I want to do it in a way that won't let you folks see the hints before we discuss them. So here we go. So here's some dynamics. First of all, what do these dynamics show? Under what sort of condition does this depict? Let me ask this. I'll be more specific. Is this model showing the dynamics when we have a fixed population? Or is this a so-called open population where people are coming in and leaving over time? Is this a fixed, finite population, or population turnover? Anyone say? Sorry? Changing. Okay, good. How do you know that? That's correct. How do you know that? Good. Yeah. Okay. So this is the number of susceptibles in blue here. They start to be everyone, just about everyone, and then it declines. If this were a closed population, a population where nobody's coming in, it's just the same people over time, what would happen then? Sorry? Okay, so they should sum up to some amount. So fair enough, and it's not clear that they all sum up here, although it's not totally clear that they don't sum up to that level. You're right about that. It's a good call. Excellent call. What else would happen though? So in terms of, let me ask this. How many infectives would you expect if we run the model out far enough, how many infectives would stay if it's a closed population? If the population is not changing, how many infectives would there be at the end? Well, okay, so let's think about this. Let's go through, and I'll just settle for the soonest of these. Hey, come on, where is this? I should have organized this better. Here we go. So here we have our equations, or here we have our stock and flow model. So if this population is fixed, if no one's coming in, suppose there's no immigration here, it's 0, and no one's leaving the model. If we run this model out long enough, how many people will be here? Or let me ask this more broadly, where will people be in the model? Okay, so if it's a really bad infection, you kind of expect a lot of people to be here, right? But does everyone have to be there? Is it possible that you could have a situation where some of the people are not there at the end? If you run it up far enough, that they'll never get there? Yes, where could they be? Where else could they be? Okay, so S and I. Now, if they're in I, what's going to happen over time? Consider a person in I. Where are they going to go over time? They're going to go eventually to R, right? So the only way there could be people in I is if there's people coming from here, right? If it's draining down. So if we think about the steady state, if we think about running it far enough that it no longer changes, it's no longer changing anymore, and again, we have no immigration here, and it's no longer changing, could there be people in I? No, because that would imply that what's decreasing? Susceptible is decreasing, right? If we have a fixed population, no one's coming in, no one's leaving the whole model, if I has somebody in it, then there must be people coming in from S, so S must be decreasing. So if we want to think about a steady state, a situation where it's in stasis, you can't actually have people in I by that point, or else S would be drained. Let me ask this though, is it possible there could be people still in S? Okay, why would they still be there? They haven't gotten infected yet. Okay, so if they're still in S, why aren't they getting infected? There's no I's. Okay, why aren't there I's anymore? They're I hear stock and flow reasoning here. Why do I say stock and flow reasoning? Okay, because I will be decreasing as long as what is bigger than what? Recovery is bigger than incidence, right? I will be decreasing. And I could decrease down to, approaching 0, as long as recovery is greater than incidence. Could there still be people in S? Yeah, it turns out, Kurt, there could be still people present in S. That's okay. There's nothing contradictory about that. What's going on is that people are recovering so much faster than they're infecting other people that I is being drawn down. Now, why is that? Why is it that people at some point might be recovering much faster than they're getting infected? In other words, there's a lot more people recovering than there are getting infected. What would drive that? Why is the number of people getting infected so small? Okay, is very low. So, yeah, this is a situation where the number of infected, we consider a given infective. Think about them over the entire course of their illness. If they infect fewer than how many people, will then the stock of I be going down? So how many people do they need to infect to kind of, when they leave the I stock, for them to leave the number of infectives no smaller than when they were there? They need to replace at least one person. They need to infect at least one person before they recover, okay? And if it's less than that, the stock of I's will be going down. And that could easily be because they're not very efficient at infecting others. They're not very efficient at infecting other people. And so the stock of I is going down. Could there be some remaining in S? Yes, it turns out there could be. If you've ever had a fireplace and you light a fire, you'll find that the fire goes out at some point. The fire goes out. Is there unburnt wood still there? Yeah, there's still some unburnt wood. You may wonder, why didn't this word burn? Well, because the fire wasn't efficient enough towards its end to burn everything. It was so much surrounded by ash and things that couldn't burn that it went out. It was unable to spread effectively. And so it is with a person who's infected. If I'm an infective and I'm in here and, all but one of you people has already gotten the illness, or all of one of you people has already recovered, then I might not be able to spread it very efficiently. I have to have a ton of contacts to spread it to even one person. And so at some point, the number of susceptibles, the low number of susceptibles will limit this. So when we have a fixed population, what we get is a situation where the infection will eventually exhaust itself. It will essentially get to the point where there's no infectives anymore. And that's what we see here, ladies and gentlemen. So we start with a large number of susceptibles. As the infection takes place, the number of infectives, shown in this red, rises, and then it turns around and decreases, okay? So let's get a narrative going. Why is it that why is it that we see this rise in the number of infectives and a decrease there? Why does it have that sort of shape? So what's occurring early on? Okay. A lot of susceptibles around, so each infective can be highly efficient.
More likelihood that the contact is with somebody who can affect that.
Exactly. And so they may be able to be in the situation where they can infect 2, and each of those 2 can infect 2, and so it goes from 2 to 4 to 8, and so on. Okay, so the number of infectives rises in that. Why is it rising? Why is the number of infectives rising based on this? Why would the number of infectives be rising? Give me, what are the conditions such the number of infectives will be rising? Okay, the average duration of infectiousness is such that what? So this stock is rising if what, under what conditions? Oh, okay, so if it'll rise if the inflow is greater than the outflow. Remember that? Inflow is greater than the outflow. It'll be rising, just like your bathtub. There's more water coming in faster than it's going out, it's going to be rising, right? So it's going to be rising. The number of infectives here rises over time under those conditions. And then, what happens at this point, this sort of point where it reaches its maximum? Okay.
More than those who are infected. So
Okay.
the number of recovered is at the same point is more than.
If it's flat, then it's what? They're equal, right? It's not rising, it's not falling, so the 2 flows must be equal. And then why is it falling later? Why is it falling down here? Why is the number of infectives going down? Because what is greater than what? Rate of recovery is greater than incidence. That's, yeah.
The peak is a tipping point.
The peak, you could informally call it a tipping point, but it's not. So it's sort of a key marker that something interesting has happened between 2 modes of behavior. So yes, I guess you could say it marks a tipping point going from an expansion phase to a decrease phase. But yeah, so I guess that would be a legitimate thing to say. And the key thing that tips it in one direction or another is the fraction of susceptibles around. So if there's too few susceptibles, a given infective is not going to be able to spread it efficiently, and it's going to be dropping. Otherwise, it's going to be taking off here. So from a standpoint of a single infective, at this point where it's flat there, what is the case at that point? From the standpoint of one infective, what distinguishes this place? What's sort of notable about this? They will infect how many people before they recover? 1, exactly 1. They'll replace themselves. And so when they recover, there's no fewer and no more infectives than when they were infected. So That's, under that condition, it'll remain flat, the number of infected. So here we have this situation, and that indeed is a key point from standpoint of tipping point. That has to do with what's called the basic reproductive cost, or basic reproductive number. The effective reproductive number, the number of persons infected will infect before they recover over the entire course of their illness. That's when it's exactly equal to 1. They're going to infect one person over the course of 1. Okay. After that, it's going to be less than 1, so there's going to be a drop in the number of infectives because they're not even replacing themselves when they recover. There's going to be fewer and fewer people remaining. Okay. So then we have this drop. And the number of infectives drops down to approach asymptotically. In other words, approach in the limit, approach in a steady state. What does it approach? It approaches, this number of infectives actually approaches 0. The number of susceptibles, does it approach 0? No. That's that wood left over in your fireplace. It approaches some limit. Not everyone has gotten infected. There were some people who were lucky, who avoided the infection. There were a lot who became infected, became recovered here for sure, but there were quite a few that remained left over. So this is an example with no births and deaths, no immigration, closed population. Does that make sense to people? Yeah.
If we change some parameters, we may have something like a negative, some oscillation.
That's right. Yes. So you could get an oscillation under this situation, but the oscillation will be pronounced in the other case. We'll see it in a few minutes. Okay. When will you get most? So you could get an oscillation in this case. For example, if people were scared by the epidemic, so they started to be more careful. So the beta term was decreased. They washed their hands more because there's more people around sick, and they are extra careful to not spread it. And then maybe as the infection is dying off, they suddenly become more lax. They become less concerned, so they're more sloppy in their behavior. You could see it actually sort of have a second peak. So that's possible. If they were really, sloppy, then now an infective for that time would start to infect more than one people again. And so you could get some oscillation if there was a negative feedback. That could happen. But the case where we see, by the way, and this goes through symbolically and sort of derives the situation. So if we consider the number of people they infect over the entire course of an illness, that's the length of time they're infected. This is reasoning about the number of people they infect over the course of their illness and the conditions under which it will be on one side or the other. So this is this tipping point where it plateaus, that was being asked about. And we see these overall dynamics. So early on, it grows quickly, and then the number and susceptible numbers are still starting to decline, but they're still high enough each infected to spread sufficiently. Over time, there's more infected, fewer susceptibles, and at some point you reach this tipping point, and you can view it from an aggregate level or an individual level. And in any case, after that, there's a declining number of infectives and susceptibles, so lower and lower rates of infection. It is notable that at this point, after this tipping point, the number of infectives is going down, but so is the number of susceptibles still. Because after all, there's still infections occurring. And so you have a drop in both the S and the I term, and that leads it to go down really quickly. What does this look like to you, ladies and gentlemen? If I watch that, so I, about 3-4 years ago, I was at a talk given by a prominent person in the health area, and they showed graphs of H1N1. So H1N1 was the flu pandemic that occurred across Canada and across the world back in 2009, 2010. So they showed graphs on the number of infective cases all showing the same decline basically the same sort of rate of speed. What does that look like to you, ladies and gentlemen? If I showed you that 2 weeks ago, what would you have said? Sorry? First order delay. What is this dictated by? So it looks, almost drew it up there, but where's my pen? Here. It looks kind of like this. What is the speed of this dictated by? This is dictated by what? If there was a mean time until leaving the stock. Yeah, exactly. So we could express this as e to the minus alpha t, or e to the minus t over mu, where this is the mean time until. And so what he was showing there, he commented, sort of saying, oh, isn't that interesting? All across Canada, you had the same drop with the same speed here. Why is that? He was wondering maybe it was something about the healthcare system or whatever. Well, it basically reflects how quickly people recover from the flu. That's what it is. This is being drained by what? Where's the first order delay that's kind of associated with this? Can anyone show me that first order delay within this? Where's the first order delay that's associated with that drop? After the peak. Yeah, just help people. Okay. But I want to get to this issue of right. So yeah, and so fewer and fewer people over time are going to get infected. More and more draining from that, so that inflow to I is very low. The outflow is dictated by the number of people on there, and it drains to basically zero. And there's still some people left over at I. But so we can see this with shifting feedback loops. The first feedback loop is associated with the outbreak. This feedback associated with the number of the spread of infection. Here it gets increasingly eliminated by sort of depletion of susceptibles, and here by the number of recovereds just going to zero. It's a negative feedback on the number of recovereds. The more recovereds there are, the more recoveries, and therefore the fewer recovereds. It's a negative feedback and it drains. Okay? So those are those feedbacks. That's great. But let's talk about the second situation. So here, and gosh, I thought I had it earlier in here. I'd like to talk about the case where we have an open population. Okay, so suppose we have an open population. How is it different? Can anyone tell me? With an open population, what do we get? So we have an open population here. How is what we saw different? How does it change the long-term behavior? Okay. It doesn't drop to what? It doesn't drop as far because there's what? The outflow is there, but now there's an inflow to it. So that's good. So the number of susceptibles stays higher. What also doesn't drop to zero? The number of infectives. Because now the number of infectives is dynamically changing. And we no longer have this issue of the infectives being unable to spread, because after all, there's still susceptibles around, right? And the number of infectives can spread. It can spread. It's like adding fuel to the fire, right? It's like the new susceptibles coming in are like fuel being added to a fire, and the fire's not going to go out. It may be at a small level or what have you, but it's at a small level. So, so I wanted to talk about this. So who can help? So this is a graph for an open population where people are coming in and people are leaving. So you'll notice that susceptible is blue, infectives are red, and this is the so-called force of infection. What do we call the force of infection? That's the chance per unit time that a susceptible will get infected, and it's C times this I plus S plus I plus R times beta. This is the chance. This is the in analogize it to alpha here. It's what we call it, force of infection chance per unit time, per week, for example, that someone will be infected. And we traditionally would give it a letter, a Greek letter, called lambda. And so we could view this as equal to S times some lambda. Okay? This force of infection is an absolutely key factor, and so we graph it out here. Okay, so who can tell me what's going on here? What happens at first? See if you can narrate to me what's going on. There's a story here. Behind this graph's or a story. What's the story? So at first, what's the situation? Lots of susceptibles and very, very few infectives. I think we started with one infected, 999 susceptibles. Okay, so then what happens? We start with that single infected. Then what happens? Okay, so here we have the red, which is the number of infectives. So you get this outbreak occurring. Now, what's occurring during that outbreak? Yeah, the force of infection is rising. Why is the force of infection rising as well? Yeah, because this I over S plus I plus R is going up, right? C and beta are just parameters here. We're assuming they're constant for now. How frequently people are meeting up and their chance of transmitting if they meet, if an infective meets a susceptible. So what's going up is I. The fraction that are infected. So that's rising too, which means that if you're susceptible, you're more and more likely to get the infection, right? So we get this infection outbreak occurring. The number of susceptibles drops dramatically. We've seen that before, right? We saw that earlier with the closed population. What's different now? Okay, so we have births equally so. Immigration. What's that? Okay, there's a fountain of susceptibles. Yeah, that's right. There's a new source of susceptibles. So what does that change? What's the most obvious thing that changes here? Okay. So what do we see happening that we didn't see before? Susceptibles increases. Why does it increase? Under what conditions would the stock of susceptibles increase? If the birth rate is higher, do I have a nice? I've got to have that handy. If there's more people coming in per day than are getting infected per day, the number of susceptibles will rise. Now, what happens as the number of susceptibles rises? What's inevitably going to eventually happen? Well, then more people are going to get infected. You're going to get the secondary outbreak. But let's talk about some of the details of it, because it's a nice illustration of stock and flow reasoning. So I'm going to pose to you some questions. Okay, so here's a question. Why is it that the number of susceptible here is rising, but the number of infectives is still going down? So the number of susceptibles here is rising. This blue line, after this point, about 50, is rising up. Why is the number of infectives still going down all during that time? Isn't that making the infectives more efficient? Okay, yes, there's a delay. Why is there a delay? Under what conditions would the number of infectives be declining? Okay, so that's a good way to put it. Let's put it at a more mechanical level of stocks and flows. The number of infectives will be declining if what is greater than what? Recovery rate is greater than the infection rate. Now, so here susceptibles is rising. What does that tell us is also rising in terms of infections? Yeah, the inflow. The number of infections per unit time is well, okay, so we have to be careful here. Certainly the number of susceptibles is rising. So the number of infections occurring per unit time may be rising, although the number of infectives is still declining. So The fewer infectives, there's more susceptibles that may or may not be rising, but the recoveries are still going on. So you're getting a drop here in the number of infectives for a while, even though the number of susceptibles is going up. The number of infectives is going down. And what does that allow susceptibles to do? Yeah, to sort of rise to actually quite a high level, actually quite an unsustainable level, a level well above its sort of endemic level. And the fact that a number of susceptibles rises that far, that allows what to happen? So why is it that the number of infectives at some point turns around here? Why is this plateauing here? Why is it stopping going down? Under what condition would the number of infectives be constant over time? Not be increasing, not be decreasing. If what? Yeah. So now at that point, the number of infections equals the number of recoveries. And what's still going on at that point, just after time 100, what's still going on here? Susceptibles is rising, right? So you're having the same number of infectives, susceptibles rise, same number of infectives, ladies and gentlemen. Number of susceptibles is rising. What's that going to do to the number of people getting infected per unit time? It's going to be rising, and therefore, but if the number of infectives is staying constant for the moment, what's that doing to the number of recoveries? It's staying constant. So, in short, the number of infections is going to go up, but the number of recoveries is not going up. So you start to see a rise in the number of infectives. In other words, the outflow is staying more or less constant here, but the inflow is rising, so it's going to rise. Number of infectives is going to rise back up, and it's rising. Now, here we see the number of susceptibles turn around. It plateaus. Why is it stopping going up then? Because what? Under what conditions will it no longer be going up or down? If the infections equals the rate of births, for example. And so it's no longer rising there. The number of infections is sort of keeping it constant. And then it's starting to decrease, but even though it's starting to decrease here, the number of infectives is still rising. Why is it rising? Well, the number of susceptibles around is easily enough to let the infection transmit efficiently and to exceed the number of recoveries, so the number of infectives is going to be rising. So, ladies and gentlemen, remember the whole concept of delay here. So here we have susceptibles and recovereds arranged. It's almost like an aging chain. Susceptibles here, susceptibles, and then infectives, and so on. And so we're going to get the change in infectives. The peak in infectives is going to here be somewhat lagging the peak in susceptibles. And we're dealing with stocks and flows. We have to remember, we may be changing the flow, but it takes a while for the stock to respond. Here, at this point, here, the number of infections per unit time exceeds the number of recoveries per unit time, this point here. And as a result, the number of infectives is going to go up, but it takes time to go up. And similarly, the number of susceptibles has peaked here, and that's going to be leading to a peak in the inflow to the number of infectives, but it takes some time for that to actually translate into the stock, the value of the inflows to be sort of maxed out. Susceptibles has to decrease here some, and the recovery rate has to increase here. So here we get a secondary peak and then a tertiary peak. So we get these sort of peaks, successive peaks. Now, later in this class, we're going to see some more pronounced examples of this in an agent-based sort of way. But what you see is spacing between peaks, successive peaks associated with this infection. And in fact, if you look at many conditions, that's exactly what we see. So this is inter-epidemic period, for example, for measles or rubella or mumps or polio or chickenpox and smallpox that have been empirically observed. In other words, you do see these sort of swings over time. And in fact, if you were to look for Saskatchewan, for example, what you will see in that case, and I think I've got a graph of it here, is you'll see. Don't tell me I cut that there. So give me a second here. It's in my PowerPoint, I think. Okay, so for something like measles and mumps, you will see exactly that phenomenon. So these are from England. This is pertussis, I think, for England and Wales, and this is for Saskatchewan. This is before vaccination, but you will see these successive peaks. Help me explain these peaks, ladies and gentlemen. These look a little bit different from what we've just been looking at, but they're the same basic phenomenon. They're just more pronounced. And we'll see later with an agent-based model, we'll get some understanding of why they're more spiky than what we've just been looking at. But they're the same fundamental phenomenon. Why do we see them? Give me a narrative. One here is red, is measles, and the other is mumps. So this is from Saskatchewan over the period of decades. Why do we see these sort of break? Why do we see it in England too? Why do we see it in Wales? Help me understand what's going on. Give me a narrative for why we'd see peaks. So I'll tell you this. I'll give you some hints. So first of all, measles and mumps are communicable diseases. So they're kind of like the infections we just were looking at. They occur predominantly, almost entirely in kids during these periods. Because older adults, almost all of them had them before, so we were recovering.
Kids go to school, a lot of kids get
Okay.
sick.
Yeah?
And then, because there's no susceptibles anymore,
Yeah?
it drops.
Yeah.
And more kids go to school, and a lot of kids
Good.
get sick.
Good. So yeah, what we see year to year is fundamentally the same thing. The susceptibles are depleted. You know, it's this thing we saw here. Susceptibles are depleted. The susceptibles are now too small, too low, too few in number to maintain the infection. So the infection sort of reaches a low ebb. The infection can't maintain itself. It can't sustain itself. It's too inefficient to transmit. A given infective will infect fewer than one person before they recover. So the infection, there's too few susceptibles around, so the infection sort of goes into abeyance. It goes into this kind of low mode where, you know, it's not really evident. It's only in a few cases around. And what is that timing, the fact that it's kind of disappearing during this time, it's at very, very low levels, what does that allow to happen? It allows recovery of susceptibles. So it allows the stock of susceptibles to grow. Now, for kids, suppose we're talking here about kids, 0 to 5 or so years of age. How quickly does that stock of susceptibles recover? We consider kids 0 to 5 years of age. How quickly does that recover? Yeah, about 5 years. It's more or less totally recovered. So it reflows really, really quickly. Babies are born and the number of susceptibles can build up quite quickly. And meanwhile, the infection's kind of not yet caught up. And then, at some point, the number of susceptibles rises to the point and the conditions are right in terms of crowding in schools and so on, that you start to get the ability for the infection to transmit again really, really quickly. And it's a bit of a stochastic thing exactly when that occurs because there's so few cases. But then you get this initial one, decline, the number of susceptibles is building up, and then boom, it can do it again, and then decline, and then you get in this case it's a small outbreak, and then so it declines, and then a big outbreak. So this is a stock and flow dynamics. Whether you describe it at an agent-based model in terms of a model, or whether you describe it using a system dynamics model with stock and flows, it's really helpful to understand it as a stock and flow phenomenon. You get a depletion of the number of susceptibles that allows the infection to go into a low mode where it isn't really spreading, the number of susceptibles rises up, and it rises up to a non-sustainable level where the infection is then capable of efficient transmission. And boom, you get another round. Boom, you get another round. Low numbers and the small sample counts associated with that will help us explain later, and percolation effects will help us explain later these sort of pronounced variation. But that's the basic gist of it. So when we see these statistics on inter-epidemic periods for different types of bugs, different types of infections, then we can appreciate sort of where they come from. They come from the stock and flow dynamics. And you'll notice that associated with these ones that have these pronounced swings, you look over at the average age of infection. When did kids get infected by these things? Measles, 4 to 5 years old. In some other countries, these are countries in Africa, 2 years old. Rubella, 11 years old. Mumps, 6 and 7, 8 to 9. So again, very quick recharging of the stock of susceptibles. So year in, year out, ebb and flow due to the stock of susceptibles. Yes? Sure.
How stable is the oscillation in the variation? So if I change C and D and over what potential range in your sort of input, parameter space or whatever, are you going to get oscillation, and how often is it just going to die out? Because it almost went down to zero.
Yeah.
So if it did hit the zero, there would be no oscillation. It would just die out.
Yeah.
Go back out.
Yeah. Okay. So that's a great question. By the way, I have these all labeled, and you folks can refer to them. These. Okay. So, sort of how stable is it? Well, let me.
How wide ranging would be the oscillation? Because no doubt there'll be other diseases that have different values for C and D with the same SIR kind of thing.
Yeah.
And they'll either just die out, or they'll massively infect and kill off the population of Black Death. I don't know.
Right. So I don't know that I have a great answer to that. Let me ask this, though, because this will get really well into our coming lecture, probably for Thursday. Ladies and gentlemen, will the number of infected here ever go to fully zero? Let me ask this. I'll back up for a second. For a first order delay, will the value of x here ever go to zero? Under what conditions? Okay, but suppose that this starts. Suppose this starts at 1, right? And suppose, for ease of thinking about it, we have a mean time in the stock of mu equals, sure, we could just say mu equals 1, in fact. And so the formula here is x over mu. We'll get a drop off like this. Will be a drop off of e to the minus t. When is e to the minus 2 equal to 0? Under what conditions? Well, equal e to the minus 2. We start with one person infected. T equals infinity. Yeah. E to the minus t equals 0. You can, you'd be tempted to take the log of both sides to get minus t equals natural log of 0, but this is not defined. It's minus infinity, and so t equals infinity. So basically, it's not going to go to 0 in any finite time in one of these models as an approximation. Now, that's all fine if you're dealing with giant populations that are well mixed, but I think what you're pointing out is that in reality, there's, in a real population, there's going to be limits. There's going to be discretization in terms of the number of people who have it. And it could go to 0 in that case, right? And we actually could, in one of these models, treat it, if it's below a certain threshold, treat it as 0. We could do that. So Kurt in Vensim there, which he's probably frothing as we talk, he could go and he could set it so that, this is, we can treat the value of the stock as something like, the maximum, the max of okay, so how do we do this?
Create a really fast recovery time.
Okay.
Get up with them scratch. I don't know if it's the same
Yeah.
model you built, but I'm getting so much faster.
Okay.
Okay, it's not 0, but it's minus 44.
Okay, yeah, so that's pretty close then, right? Yeah. So you could have in Vensim, the easiest way to probably do this is that if then else of x less than less than 10 to the minus 8, you could treat it as a 0, otherwise treat it as x or something like that. So you could actually impose a limit where essentially you treat it as 0 at a certain value. In terms of how stable it's going to be, Kurt, sort of the oscillations, you can actually derive what the interoscillation, if for a simple model, you can derive what the interoscillation timing is going to be. What's the timing going to be between these successive peaks? But a lot of what goes on in a realistic situation like this is that there's stochastics. There's vagaries of particular person and whether they're able to transmit it over their particular networks. There's sort of localized effects. And so you're not going to get the, you're not going to get exact smooth curves for this. And in fact, you see these sort of spikes that are different from year to year. But we're going to see exactly this in a later model. Okay, we're going to see a model which can reproduce this quite well. And again, it exhibits stock and flow behavior. And even though it doesn't seem to look exactly like this is the underlying governing factor. This is sort of really what's driving it. It's just that there's also small numbers, and Kurt's right to put his finger on that. Okay, so any questions about this dynamic? Yes, go ahead.
For example, right now we have a period for each shock disease. We have a period
Yep.
that's after, for example, a recovered person
Yep.
is immune for a period. Yeah.
Yep.
If we have for some disease, this period is long enough,
Long enough, yeah.
and we prevent by using vaccination and
Yes.
things like that,
Yeah.
prevent inflow.
Yes.
We can, maybe,
Eliminate the.
limited time.
Yep.
And
That's right. That's exactly right. And that's what this tipping point has to deal with. I wish I could present this. This is another way to view what we've just talked about going on, where we have susceptibles and infectives on what's called a phase plane diagram. So we at any given point, the system's at one particular place, it has a certain number of susceptibles and a certain number of infectives, and it's evolving over time. The number of, as I'm drawing this, what's the number of susceptibles doing? It's decreasing, and the number of infectives is, okay, and then what happens here? Okay, now the number of susceptibles is doing what? Decreasing, and the number of infectives is decreasing also. And then you got, this is what it kind of looks like in a so-called phase plane diagram. And you'll notice that with different birth and death rates, you get sort of different shapes of this. So this is with a very high birth and death rate, very rapid convergence to a higher level of so-called endemic infection. This is where the infection stays present. Here's with a smaller birth and death rate, lower value, it takes a bit more iterations to get there. Here's a smaller version yet. And here, I think what Kurt was saying, that you can get very, very small levels of infection. You get big oscillations in the number of people infected, and it goes down to very, very small levels of infection, and then pops up again, and then pops up again, etc. Yeah.
What affects the arrows? Because each of the
Oh.
blue traces is a different birth rate.
There's a different birth rate. The arrows basically reflect, so this is, again, it's called a phase plan diagram or state space diagram. And the arrows basically here tell it, like, if you were to land here, if you were to pick out a situation where you had this many susceptibles and this many infectives, where would you go next? They kind of drag. So
Is that
here,
determined by like C and D? Or
yeah,
something?
yeah, it's determined by D susceptible, D infected. So the time derivative, so it's the left-hand side of the differential equations.
Does that mean that the blue line is not actually like functionally separate from the arrows?
It just follows the arrows. You could think of these as kind of where the stream is flowing at this place. So over this, the stream, there's a current in the stream that's kind of pulling this way. And so if we drop a marble on the blue line, it will roll where the blue line has. It'll be guided. That's not a great analogy. A marble in a stream wouldn't do too much. But a boat. If we put down a paper boat.
It's a floating boat.
That's right. So Curious Gorge's boat in the stream, you put it down, and it floats along and sort of would be drawn down here. And this is a whirlpool. This is a vortex.
And then we go up again?
Well, it's going up here, and then, but this is entrapping. So this is the endemic situation, which corresponds visually to exactly this. It sort of oscillates, and then it sort of stays here. Now, the interesting thing here, which I think you're maybe getting to, is that, ladies and gentlemen, when we see this attracting to these points have there's a notion of, how many of these points are there? These are called fixed points. These are points where it's in equilibrium. At this point, it's no longer changing, actually. And what does it mean for it to no longer change, ladies and gentlemen? If I told you that this model, this model is no longer changing. Everything is the same. S, I, and R aren't changing. What does that tell you? Immediately. Yeah, all the inflows and the outflows have to be equal. Everything has to be in balance for each stock in turn. And with an open population, there should actually be deaths coming out of here as well. But for an open population, we can get that sort of situation where these things are all in balance. At this stage, the number of susceptibles is no longer changing because births equals infection rate. Moreover, the number of infectives aren't changing because infection rate equals recovery rate. And the number of covered people is not changing, even though it's not shown, because the rate of recoveries must equal the death rate for that. And I should have mentioned death rate for the other stocks as well. Okay.
That's because of the negative feedback.
Yeah, that's right.
It has to.
The negative feedbacks are stable. They're gonna lead it to a situation of stability. It's all gonna go towards a situation of stability. So these are called fixed points, where it's no longer changing. However, ladies and gentlemen, there can be stable and there can be unstable fixed points. This is a stable fixed point. It sucks it in towards it. Just like that. And it sucks it in, and it's stable there. And any perturbation, what's going to happen? If I knock it out a bit, what's going to happen? It's going to go back. well spoken, young man. So that's right. It's going to go to the same vortex place. It's going to go to the same underlying place. So, ladies and gentlemen, if I had someone come into the Saskatoon airport here, with infection, with an infection, what's going to happen? Well, at this equilibrium, how many people is an infected person going to infect before they recover? One. At that equilibrium, that's the situation where it's in balance. That's the situation under which, in fact, the count of people infected is no longer going to be changing. And so if we had someone come into the Saskatoon airport with infection, they might infect one person before they recover, in which case there's no net change. They're going to infect one person before they recover, and essentially it's not going to cause an outbreak. Maybe they'll infect two, but it's not going to be efficient enough to transmit broadly. They might infect zero, and on average they'll infect just a single person before recovering. If we brought in 100 people who are infected to the Saskatoon airport, now these people will infect some people around them, but they're going to lower the fraction of susceptible, so it's going to be brought back into balance. The number of susceptibles will be going down too, and so they're going to bring it back into balance. So it's very stable at that point. The other type of equilibrium, though, is what's called an unstable equilibrium. Give me an example of an unstable equilibrium. Give me a situation where there's no change, but it's terribly unstable. Think of...
Well, it's like you're talking about hill.
Good. Give me a situation involving a population such as this one.
The infection dies out.
Okay,
The infection dies out, and there's only a bunch of susceptibles because
Good.
there's growth everywhere.
good,
And one person in the airport is going to start off.
good. Exactly. So if we have 0 people infected, everyone is susceptible. Okay, so let's think about that. Everyone is susceptible, no one infected. How many infections are there per day? 0. Why? Because there's nobody to infect them. I is 0, right? No infections per day. How many recoveries are there? 0. And would that system, in terms of those things, would that be an equilibrium? Yeah, sure. And if you had a number of deaths such that it equaled the number of births coming in, everything will be in equilibrium. Will it be a stable equilibrium? Will it be stable? If there's no one infected? Why not? Because if we bring one person in, boom, the fire takes off. It's like a loaded fireplace. You throw in a match, it takes off. So that's, ladies and gentlemen, an unstable equilibrium. Now, how can we find equilibria in terms of the underlying differential equations? These are the differential equations. This says what's the number of change in the number of susceptibles per day, total number of susceptibles, total number of infectives, total number of recoveries. Where are these terms coming from? Well, this is recovery from infection, and that's coming from here. It's a flow out of I, so it's associated with a minus. It's a flow into R, so it's associated with a plus here. Similarly, the blue, you'll recognize that from the thing, and here it's S plus I plus R. This is a flow out of susceptible, and it's a flow into infective, so it's minus from susceptible plus here. So how do we determine fixed points? Situations where the stock is no longer going up or down. This stock not up or down. S dot is then 0. So we can put zeros over here. We solve for I, S, and R in terms of the parameters. And we can do that. And we can get, there'll be equilibrium. And in general, ladies and gentlemen, there'll be equilibrium for an open model. There'll be several equilibria. So let's just go here. There's a disease-free equilibrium where there's no infectives. The entire population is susceptible. Is that an equilibrium? Yeah, it's an equilibrium. There's an endemic equilibrium, which is the steady state produced by the spread of illness. That's that situation we just saw where it's going some small duration. This is stable. Why is it stable? Because the system's in balance. We bring one person in, and we brought back into balance. So the stability of these equilibria depends on parameter values. And a lot of the goal, and this is what Fahad was asking about, a lot of the goal of the public health system for infectious diseases is to make it stable, to make this, and even the disease-free equilibrium, such that the infection won't spread. And you do that by vaccination, for example. So you have so many people around you vaccinated that if I'm sick, I still can't spread the infection effectively. I still won't infect more than one person before I recover. And at that point, it will be stable. Okay? Yeah.
Are the measles and the chickenpox
Yeah.
and those
Yeah.
diseases, are they just never in equilibrium? They're never at zero, but they're never just kind of spinning down into endemic form.
Right. So it's a good question. It's a more complicated situation there. There is what's a notion of what's called the dynamic equilibrium. Okay. Now that sounds odd, but the point is it's just repeating over and over again.
You're showing around the sun.
Precisely. So it's not strictly a fixed point. It's not a situation where everything's in balance, nothing is changing. But what it is a cycle, say, around a fixed point. And you just get a recurrent sort of pattern again and again and again. Think about a clock ticking. Think about the patterns of lynxes and hares. The population go up and go down, go up and go down, and it's just a regular sort of cycle that's occurring around some point, and it's recharged by births and depleted by infection spread. Recharged by births, depleted by infection spread. So that is actually a situation which you can get in, and you can describe it mathematically. Instead of going to some fixed point where you're no longer changing at all, instead you're going in an orbit. You're going in an orbit around this sort of place, and you do see change, but it's repetitive. It's something which is periodic, and we can see situations like that. The equations we're dealing with here are simple enough; we won't see that, but you can in fact have situations where that's the sort of equilibrium you get set in.
When I think about it, it's probably most of those, like,
Yeah.
childhood infectious diseases
Right.
are like
Are like that. Now, however, what's happened is because of vaccination, we have changed it so, at least for a long time here in Saskatchewan, we had a situation like this, where you have one person who has measles that come into the population, from another province or from overseas or what have you, and that person is they're unlikely to even replace themselves, when they recover, and because they're surrounded by so many vaccinated people. And as a result, if you look at the mean number of people infected over time, it's actually declining over time in terms of sort of your expected number of people that will have it. Okay, maybe they infect 2 people. They're really in an unlucky situation, they infect 2 people, but those people aren't going to be able to pass it on efficiently. And so you get this situation where this disturbance leads to a decay in the number of people with it. They come in, on average, they're not going to infect even one person, and so the system just brings itself back into equilibrium, right? And that's what we're trying to do through vaccination. And I have descriptions within this on the vaccination side, and here we can actually talk about some of these classic components. So I'm going to need to decide something because we're going to need to break for today. So I would like to know how many people here. We have 2 choices for next time. Okay. And I'd like to see a vote of hands. if you're really enthusiastic, you can vote with your feet as well. Okay. So the question is, next time we could go with Venson and we can build up. We can do it actually quite quickly, building up the actual model, and we can do a bunch of experiments. And for example, we could have a vaccination. We could examine a vaccination campaign, how we'd represent that, and actually try different vaccination rates and understand how it affects things, and see how the equilibrium has changed in the presence of vaccination. And you get to build up a model from scratch and leave with some pretty interesting results. Alternatively, we could go on and start talking about the next significant form of modeling we'll be looking at, which is agent-based modeling. How many people would like to try building up a model from scratch together during the next class? Okay. Okay, your feet? Okay. How many people would like to go into agent-based modeling next time? Okay. 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 So I think based on that, we will. Yeah. The ayes have it. So we'll try building this up, and maybe what we'll do is we'll use this example then to within the context of an agent-based model also, so we can kind of see the contrast. Although we probably won't do the agent-based model. We won't do the agent-based model next time, but we'll see if we can do it in our introduction to agent-based model. We could have a cross comparison. Okay. So that will be next time. So come with your machines. If you don't have a machine, you want one delivered, let me know. But otherwise, come with Vensim PLE, and we'll build this up. Okay? Okay. So thanks very much, folks. So some of you have asked for meetings related to projects, and I'm glad to do that. And I'm going to be meeting with some students next week. I'm glad to do it after class here as well. So just let me know. Okay?